आज के वीडियो के माध्यम से हम लोग IS 456 में बॉन्ड एंकरेज एंड डेवलपमेंट लेंथ ऑफ स्टील क्या होती है, क्लास 26.2 में दिया गया है, उसकी स्टडी करेंगे। बॉन्ड बहुत ही इम्पोर्टेंट एलिमेंट है, सो दैट कंक्रीट और स्टील के बीच में ऐसा बॉन्ड होना चाहिए दे शुड एक्ट टुगेदर, दिस द स्टील शुड नॉट स्लिप आउट फ्रॉम द कंक्रीट अंडर द लोड। फर्स्ट पॉइंट यही है कि बॉन्डिंग बिटवीन द कंक्रीट एंड स्टील should be proper, so that section remain plain even after application of load. So this steel should be anchored properly in the concrete. Second is the length required. The length of member required to develop full bond is known as anchorage length, and the bond is measured by the bond stress. So first point is bond between concrete and steel is very important, and essential. The concrete and steel act together without fail without any slip under the applied load. So the concrete and steel should act together without slip in loaded structure. Now, the another important question is the length of member should be such that should be anchored in the concrete such that it should not slip. So, length of member required to develop full bond is known as anchorage length. So, length of member required to develop full bond with concrete in tension is known as anchorage length. Length of steel member or rebar member is required uh, uh, in such length that it should be embedded or anchored in such length that it should develop full bond with the concrete, so that slip from the concrete doesn't occur. So the length of member required to develop full bond with concrete in tension is known as anchorage length, and the measurement of bond is done with the bond stress. The measurement of bond is measured by bond stress denoted by tau bt. So Three important points in this slide we have seen. One, the bond between concrete and steel should be such that steel should not slip out from the concrete under the load. Second, the length of member should be such that it should develop full bond with the concrete, so that length is known as the anchorage length. And third, bond is measured with the by um, this uh, tau, measured by the bond strength, that is tau. So we will study in detail in the coming slides. So this is a concrete block of say dimension A into B, in which a steel member is embedded, anchored. So how much is length? How much length is required, so that due to pulling force of T, this steel should not come out from the this concrete. So the problem is how much tensile force required to pull out this from the concrete, or we can say what is the balancing force between this, so that steel should not come out from the concrete. So we know that this tensile force will depend upon the cross sectional area of this steel and multiply by the uh, tensile stress, sigma s. Whatever sigma s is developed, if we multiply by the cross sectional area, we know the tensile force. So tensile force is given by T is given by the cross sectional area of this, that is pi by 4 into this dia is phi, so phi square into the bond into the tensile stress, sigma s. How much is the tensile stress developed due to the force of T? So that is sigma s. Now this force will be registered inside the concrete by the bond stress, bond between this steel and the concrete. Whatever bond has developed, like in the case of high strength deformed bond, it will be rifts. That rifts and this concrete will develop a bond, and due to this bond, this will resist pulling out of the steel. So how much is length required to uh, keep this inside the concrete without any slippage? So we can find out the resistance force. How much is the resistance force required? That resistance force will be the bond distance between the this member steel and concrete, that is given by tau Bd into the perimeter, nominal surface area. How much surface area will be required to resist that force? So that is surface area will be 2 pi r, or we can say pi into phi into this length. This length is nothing but development length. How much length is required? So this length is LD. Now since to keep the equilibrium, this resisting force will be equal to the tensile force applied. So we can equate pi by 4, tensile force pi by 4 into phi square into tensile stress sigma s equal to tau Bd bond stress into pi phi 2 pi r, we can say uh, 2 r is d, so pi phi into development. Now we need to determine, we know the how much is the bond stress between the concrete and the steel. It is given and it is known. Generally, bond stress increases with the force, goes to the maximum, then come to the zero. We take for all calculation purposes the average bond stress tau Bt, and it is given in the IS 456 table itself. How much bond distance should be taken for the particular grade of the concrete. So now LD will be pi by 4 into phi square, pi d square, pi by 4 d square into sigma s upon tau bd into pi phi. So simplifying this phi will get cancelled with this phi will get cancelled by this, and the remain will be phi into sigma s upon 4 tau bd. So development length will be required to keep this steel inside the concrete without failing, without slipping. Is this: if we keep the development length LD equal to phi into sigma s upon 4 tau bd, where phi is nominal diameter of the bar, sigma s is stress in bar considered at design load. Whatever design load are, uh, if it is UDL, point load, or whatever load is coming at that particular section, how much the stress has developed, and then how much length of bar will be required to resist from the slipping out. Then tau bd is bond stress. The tensile member has to be anchored properly by providing additional length on either side of the point of maximum tension. If in any member we find out the maximum tension is here, then still the development length will be required for anchoring equal to phi sigma s upon 4 tau bt. Then because of this tensile force, it will not slip. So hope this will clear how much the development length is required uh, against the tensile force to keep bar without slipping in the concrete. Now let us see the one example. This is the beam loaded with UDL. So maximum steel will be required. Maximum steel will be required at the center, and after certain length, say at section 1 curtailment is to be done. 50% bar say is to be curtailed at section B. So how much development length will be required beyond section 1 to keep bar in position without slipping in the tensile force? Because this bar will be, if UDL is there, this bar will be under tension. So how much is the length development required to development length of steel is required to keep bar in the position so that bar doesn't slip? So here also we can apply the basic this thing. Now this, you can see, this is the free body diagram of this LD. So this is the force. This is the force will be pulling. This T force will be pulling this bar at this section. So we know the how much the tensile stress is there. Sigma s, the cross sectional area of this steel, pi by 4 into d square. How much length LD is required? LD into how much bond stress is developed with the concrete with this steel, that is tau bt into pi into phi. So again we can find out the development length. Phi will get cancelled here. This phi will get cancelled with this phi. So this will be phi sigma s upon 4 tau bt. So beyond this point, this is the maximum steel required, say 6 number. 3 number needed to be curtailed here at section 1 and this LD length will be additional length will be required of the bar to keep the safe additional length, so that this particular steel 3 number which has been curtailed here do not slip from the concrete under the load. If we see the combination of column and beam, which is very important, we provide the Anchorage development length, because at this junction there will be maximum stress. There will be maximum stress, so we need the sufficient additional length of the bar to keep the structure in equilibrium. So we calculate similar way how much the development length is required, phi sigma s upon 4 tau Vd. Since there is a restriction, in the column, it cannot go in this way, then it is bent, and the hook and bend allowance Anchorage length is calculated as per 2502. So this is the length required. It has been bent inside the column. Again, top bar is also bent inside the column to give this length is a LD, development length in this case, in the case of column. This is the development length. Now, bond stress in IS 456, what is the bond stress for different grade of concrete is given in the table. We can directly use this table for taking the values of bond stress. For grade of M20, it is 1.3 Newton per mm square. For grade of M25, it is 1.4 Newton per mm square. For grade of M30, it is 1.5 Newton per mm square. For M35, it is 1.7 Newton per mm square. And for M40 and above grade, it is 1.9 Newton per mm square. Since we know that development length is LD is equal to phi sigma s upon 4 tau Vd, where phi is the diameter of steel, and tau Vd is bond stress between the concrete and steel. Now, tau Vd bond stress is increased by 60%. Increased by 60% if we are using HYSD bar or TMT bar as given in the 1786. So it will be increased. The deformed bar conforming to IS 1786, these values shall be increased by 60% because it is in denominator. So increasing to 60%, the LD will be, because it is inversely proportional, so development length required will be less. LD is inversely proportional to tau Vd. Since in case of TMT and HYSD bar, it will be increased by 60%, the development length will be reduced. If the bar is used in compression, this is in the case of tensile, and these values are given for the plain bar. These values are given for plain bar. If we are using TMT or HYSD bar, the bond stress, these values should be increased by 60%. Further, these value again increased by 25% if these bars, YSD bar or TMT bar, is used in the compression. Means if we are using TMT bar, we increase 60%, and then again bar compression, the value of bond stress for bars in tension shall be increased by 25%. Whatever bond stress we got for the TMT bar by increasing 60%, further it should be increased by 25% for using in the compression. If it is in the case of mild steel or plain bar, then same value can be increased by 25%. So this is the table given in the IS 456, can be directly referred from there for getting the value of bond stress. Now let us solve one question. Calculate the development length of 10 mm dia bar for M25 grade concrete that provide stress in bar at section of design load is 30 MPa. Sigma S is already given, 30 Newton per mm square. So find out the development length. We know the development length LD is given by diameter of bar into stress developed in steel divided by 4 tau Bd. Now here we consider plain bar. So phi is given in the example 10, sigma s is 30, 4 into tau Bd. Tau Bd we can get from this table, volume 25 grade. Volume 25 grade, it is 1.4. It can be taken, the screenshot can be taken from this. So this is 1.4. So 4 7 28, and so 75 divided by 1.4, 75 divided by 1.4 equal to 53.57. The development length is required 53.57 mm. Now if this is TMT bar, then it will be LD will be equal to 10 into 30 divided by 4 into 1.4 into, again it should be increased by 60%, 1.6. So value will be 10 into 30, 4 into 1.4, we've got 53.57 divided by further 1.6. So 53.57 divide again 1 point by 1.6, we get 33.48 mm. So if we are using the TMT bar or QISD bar, we get the reduced length as it is clear from this solution of the example. So in this video we had studied what is bond, why it is important, what is bond stress, what is bond values of bond stress for different grade of steel. We also studied how to calculate the development length of the any bar, which is given by development length is given by diameter of bar and the stress developed, and then divided by 4 into tau Bd. So at any maximum tension point, we should determine how much the anchorage length required to keep bar in the equilibrium, so that it should not slip into from the concrete. So by this I understand कि डेवलपमेंट लेंथ एंकरेज लेंथ डेवलपमेंट लेंथ के बारे में क्लियर हो गया होगा. फर्दर वी विल बी टेकिंग मोर एग्जांपल्स on the development length in coming up video. Thank you. Thank you. This can be noted, and it is also given in the IS 456, and this may be important how to determine the development length for any bar by equating the tensile force with the resistance force developed by the concrete due to bond between the concrete and steel. So that is we know the tau Bd given in the IS 456. We know the development length LD, and then pi d 2 pi r circumference of that steel. So we can find out how much the length should be anchored beyond the maximum tensile force to keep the bar in the equilibrium. Here also it is given the tensile member has to be anchored properly by providing additional length on either side of the point of maximum tension. कोई भी टेंशन पॉइंट है उसके दोनों साइड में ये प्रॉपर डेवलपमेंट लेंथ होना चाहिए, so that because of force the steel should not slip from the concrete. Thank you.